Let's take a look at a special case of the work and kinetic energy equation. Let's assume that the net force is equal to a constant, and therefore mass times acceleration is equal to a constant. And we'll keep everything one-dimensional just to make life simple. So when that takes place, we have 1/2 m v1 squared plus the integral of ma dot dr, integrating from r1 to r2, and that's going to equal 1/2 m v2 squared. But this integral becomes much simpler. The integral of ma dot dr will become the integral of ma dx, integrating from x1 to x2, when I consider everything to be one-dimensional. And ma is constant, so this is equal to ma times the integral of dx, integrating from x1 to x2. But that's just equal to ma times x, evaluated from x1 to x2. Well, when I substitute that into the equation, you'll see I get 1/2 m v1 squared plus ma times x2 minus x1 equals 1/2 m v2 squared. So the masses will cancel out on all sides, and I can multiply both sides of the equation by 2. Once I've multiplied both sides of the equation by 2, this becomes v1 squared plus 2a delta x equals v2 squared. And you may recall this equation as one of the equations that we used when we talked about constant acceleration equations. In that case, it might have been v0 squared plus 2a delta s equals v squared. It's the same idea. We start off with some initial velocity v1, and actually initial speed, it's not even a vector quantity because of the square, plus 2ax equals the final velocity squared. So that equation, which we came across very early in the book, is actually a restatement of the work and kinetic energy equation in this special case. Another thing to consider then is the work done by individual forces. The last set of equations that we've been using, you've always noticed the net force inside the integral. And that's going to be true whenever we're talking about the work and kinetic energy equation. That equation is only valid if we're talking about net force. We can discover what the work due to any individual force is with the same equation. So if there's several forces acting on an object, for example, if I'm looking at an object on an inclined plane, and we'll assume friction is part of this. There's a gravitational force, mg. There is a frictional force, Fk, if I assume it's sliding down, it's kinetic. And there's a normal force. I can examine the work done by each of these forces. So for example, looking at the work due to gravity, this would equal the integral of mg, which is strictly in the j direction, minus j direction actually, dotted with dr, and dr is going to be down the incline. But given the dot product, only the displacement in the j direction is of any importance because of the way the dot product works. Remember that dr is equal to dx in the I direction plus dy in the j direction plus dz in the k direction. And so since this is a j hat, only the y component even comes into play. And mg is constant, so that comes out of the integral, minus mg times y2 minus y1. That's the work done by gravity. The work done by the frictional force will be the integral of minus, well, of Fk dotted with the displacement. These are both vector quantities. But Fk is up the incline, the displacement is down the incline, and so this will very simply be minus Fk, since it's constant, times delta L, where delta L is along the incline, that total length that it slides along the incline. Then the other interesting force is the normal force. Of course, it's the only other force at all. But the integral of F normal dot dr, this is going to equal 0, because notice the normal force is perpendicular to the surface, and dr is along the surface. Everywhere in there, it's equal to 90 degrees, and so there is no dot product other than 0. So the normal force does no work in this scenario. Now, work in kinetic energy for a system of particles assumes that there are forces acting on all of the other particles. When we talk about momentum later on, we'll see that internal forces never change the momentum of a system of particles. But that's not true when we talk about work in kinetic energy. Now, let me give you a real brief example. Let's assume that we have an object here, and this could be myself, and another object over here, and this might be you. And between the two of us, we're going to have a long rope. Now that rope is an internal force, and Newton's law says if I pull on the rope, I exert a force on you via the rope, and therefore you exert a force on me. Now those forces are going to cancel each other out. So when I do this integration, and you look at that, F1 plus F2 are going to go away, but they don't, and that's the important thing. And the way you can realize this most easily is just consider for a second the fact that if we start off stationary, the sum of our 1/2 mv sub 1 squared is going to be 0. In other words, I'm not moving, you're not moving. So 1/2 mv squared for me, and there's a summation here, so that's 1/2 mv squared for me plus 1/2 mv squared for you. That's 0. But when we yank on the rope, and it doesn't even matter which one of us does the yanking, when the rope is pulled on between the two of us, now we're moving. And since the velocity is squared, the fact that I'm moving up and to the right and you're moving down and to the left is of no consequence. Yeah, those MVs might cancel out. In fact, we'll see that they do cancel out when we take just mass times velocity vector. Those are going to sum out to 0 when we talk about momentum later on. But in this case, we square the velocities. And so the fact that one's positive and one's negative is of no consequence because they're squared. And so the right-hand side of this term is not 0. And we can see that if we consider the fact that the force, let's say the force acting on me, that's up and to the right there a little bit, then my displacement dr is also up and to the right. So F is up and to the right, dr is up and to the right. The dot product of those is positive. If we look at you, it's the same force, except in the opposite direction. Your dr might be different than mine, so we'll put a y for you and an m for me. Forces are equal and opposite by Newton's laws. The drs might not be, and that's okay. But the point is that in your case, the dr and the f are also in the same direction. So that dot product is positive. So when we sum the two integrals, f dot dr for me plus f dot dr for you, those integrals don't cancel out. They might, but in this case they don't. And so the net work done is not 0. So there is a change in kinetic energy, even though we're looking at a system of particles. And if there are external forces acting on either one of us or both of us, they're also going to come into play in this term. So this force, remember, is the net force. So I'm going to look at all of the net forces acting on me, add those together, and then summation says look at all the net forces acting on you and add those together. And that might not be 0. When we talk about momentum later on, it's a different integral. They'll all go away. Now we wish to discuss power. We're going to define power here as a time derivative of u with respect to t. That is to say, the rate at which energy is changing, and a rate is always with respect to time. Or I'll even specify the rate with respect to time at which energy is changing. This is a definition. Keep in mind, du was equal to f dot dr. And so now if I divide both sides by t, and we'll assume the force is constant. If it's not, this equation isn't going to work. But if the force is constant, dr dt by definition is velocity. So power is equal to the force being applied dotted with the velocity vector. Again, it's a dot product, which means it's a scalar when it's all said and done. So power, even though vectors create power, is in and of itself a scalar quantity. All right, so force dotted with the velocity, if you know the force. If the force is not constant, then you've got to go with the fact that it's the derivative of work done by that forces or the net forces with respect to time. Efficiency is defined as the amount of power output I get from some process divided by the amount of power I put in. So the output power divided by the input power. This is a big deal when it comes to machines, either simple machines like a lever or block and tackle, or very complex machines like your automobile or your bicycle. We can also define efficiency as the energy output of a machine or a process divided by the amount of energy that I put in. Now, the energy input can be very complicated. It could be very simple, for example, forces acting on a lever or on a block and tackle system, or it could be very complicated. Input energy might be muscle power from your legs or muscle energy from your legs, although we can get really down and talk about food energy, how much energy from the food is then processed into the muscle of your legs, which allows you to propel your bicycle. Could also be complicated like an automobile. There's a certain amount of chemical potential energy in gasoline, and that chemical potential energy is used to produce energy of your car's movement. Kinetic energy of your car, for example. Efficiency would ask us how much output energy am I getting and how much input energy did I need to get there. That's where efficiency is going to be at. The maximum possible efficiency is 100%, but that's an ideal case. You'll never have 100% efficiency. When you take thermodynamics, you'll find out why that is.